For tan at negative pi fourths. So that means we need to find the derivative of tan. So that means f prime of x equals secant squared x. And then you need to find the derivative at negative pi fourths. Gross.
Sorry.
You need to have brown hair.
Me?
No. I'm trying to think of my type. I said I think I have a type. Yeah, brown.
Yeah, Lane Camden.
No.
That's your type.
No, it's not.
All right, so secant of negative pi fourths. So what is the secant of negative pi fourths? So exactly, it's 1 over cosine. What's the cosine of pi fourths?
Root 2 over 2, which is then 2 over root 2, which is 2 root 2 over 2, which is root 2.
What?
So it ends up being
Root 2. Negative. Should I just...
No, because of
4.
yeah.
Then you have to square it, so
it's 1
2.
over cosine of
Yeah.
pi fourths.
So 1 over root 2 over 2.
Which the negative really doesn't matter because you're going to square it, so it doesn't matter if it's up.
So then it becomes 2 over square root 2. Which is equal to 2 root 2 over 2, which equals root 2.
2 squared is?
4 over 2, which is, yeah, that's...
You were saying root 2.
Thank you.
But when you square root 2, it gets 2.
Square, like, multiplied by the square root of 2. That's how I...
Yeah, and then you square root 2 and you get 2.
Okay. I see it like
Wait,
that.
why doesn't the negative matter?
Because anything squared is positive.
You're gonna end up squaring.
So like if the very last thing you're doing is squaring. So it doesn't matter if the trig function is positive or negative because it's going to be positive at the end no matter what. But if it makes you feel any better, cosine in quadrant 4 is positive. So I was just saying it didn't really matter. Okay, and we actually at the very beginning need to know what is
F of 2, negative 5, 1.
I need to know what the tangent of negative pi fourths is.
Negative
So now
1.
it does matter because you're in quadrant 4, so it would be
1. No, negative 1.
negative. So my L of x is equal to f of a,
1,
which is negative 1,
negative 1,
plus f prime of a, which is
2,
times x minus a, which is
pi over 4. Negative pi
But it
over
would become pi over.
now we are looking to approximate negative pi fourths plus 0.1.
So it'd be
So this is
x is 0.1.
correct.
Thanks, Des. I'm glad.
I want to know what she said now.
She was saying Alex is actually being nice today. And then she texted Deja, okay, not anymore.
Alex, you were doing good.
So you get negative 1 plus 2/10, which is negative 1 plus 1/5, which is negative 0.8. Work together like negative 1 plus 0.8.
Oh, you're gonna end up having it in the brackets 8.1.
No.
It was all of them.
One of them was like 26 minus 27, which was negative 1. And that's just like me thinking
You
quickly.
should have
Okay,
heard
but
Dom.
the non-
you should
the
have heard
non,
the
like-
attitude Dom Mortimer gave Mr. Rock yesterday.
Oh my god.
It was worth
Oh.
You could
All right, so that approximation, what we are saying is that the tangent at negative pi fourths plus 0.1 is negative 0.8.
I think he's sexy.
So
Like, I've never said
Yes,
that
that's
before,
because.
but. No, we're not doing
Does
this
it-
again. We're not doing this again. No,
All right.
I'm actually doing
If
this.
f prime of x decreases from negative pi halves to 0, if it decreases, is that approximation going to be greater than or less than? If f prime decreases, then f of x is
Decrease to negative.
This is over.
think about where you are in the chart. Oh, well, okay.
I'm thinking back to my chart that I have in the front of my folder still.
But if it's decreasing, then it's concave down.
Yeah, that's what I meant to say.
Because the negative would come from up here. If that would be if it's positive or negative. So if f prime decreases, you're down here, which makes this concave down.
Yeah.
That was so helpful.
I thought it was
Like,
just
I literally
negative,
picture
not
in my head,
decreasing.
like,
What
But
that was like
Yeah.
probably the most beneficial. Yeah, that.
I keep it in the front of my folder at all times.
Like how I should
Can that be on the next homework check?
But as the
That's
year
true,
goes
though.
on, I feel like the chapters get more and more random to where I'm like, this was all in chapter 4, and it seems
Yeah.
like it's so different. Like,
Yeah.
like, how is this related to what we just did?
Yeah, I
The
just
shape.
well, so chapter 4 is applications of derivatives. So it's like all the different ways you can apply
okay,
them.
that makes sense.
So that's why each section kind of feels
It's
choppy.
just so random.
Yeah.
And then
All
we'll
right.
have a chapter test. Oh my god.
Okay, wait. No, go with your. Just needs to block.
Maybe it's
He's
just
not
when
Come
they're
on,
in a
Mr.
hurry.
No,
McBride.
it's not sex.
I can't eat it right now because I can't teach with one.
You still have one.
Why
My
did
mom
I
got
drink
me a
your
bag
tea?
of
Did you see what Mr.
360
Black
for
did yesterday when I buy you?
Christmas.
It has nothing to do with sex. He literally, you know, like he has like the bathroom.
Yeah, he
All
went
right,
back
we're
to the back seat.
No,
skipping.
he went in the sink and did it.
We're
He didn't even go in, like,
sipping
the bathroom.
Newton.
He used to go in the water fountain.
Oh yeah, that's enough.
All right. The last thing. So you said it's kind of random. Differentials. And oh, did you not copy down part B? Do you need that?
Doesn't matter.
Okay. So
Have you done notebook check?
differentials is a small part of linearization, and differentials in calculus actually is like this whole class. It's what her brother calls Calc 4. But like differential equation,
It is called Calc 4.
That's not
I'm
a
looking at
thing.
Pitt's classes.
differential
Okay,
equations.
it's called linearization, but it's Calc 4.
This is what we're doing is linearization.
You should tell
This is
me.
like
He doesn't know the unit circle stuff.
this is like
That
the
was not
in
that one.
this is
Yeah,
the
you don't need to know.
this is the intro to linearization. Like on a smaller scale, because then you have differential equations and they have like partial derivatives, and you look at like
Partial?
a partial derivative.
Seriously, we didn't even need to know the stuff at the beginning of the year because now we know how to take like power one. It was just like introduced.
The limit?
Yeah.
Yeah, the whole point of the limit though is so you know where it comes from.
There's no Calc 4 in Pitt's classes.
What is it called? Linearization?
There's a bunch of classes, but they're not Calc 4. I'll tell you that. I
Was
looked
there
at
is
every
there
single
such thing?
undergrad
Wait,
math.
no, is there such?
I like how
thing?
she's defending dumb. Like just like now you can just be like dumb. Calc
Dumb,
4
you're an
doesn't
idiot.
exist. Don't defend him. Just say
Look,
I looked
okay,
up
after
Pitt's classes.
Calculus
Does
3,
Calc 3
there's
exist?
Yes,
multivariate
yes.
calculus,
Which is Calc 3.
then there's matrix theory and differential equations.
Diff EQ.
Then
Intro
why
to
don't they keep on?
matrices and
Why they
linear
change
algebra,
just doing
differential
names? Why can't they
equations.
fix the numbers?
Because a calc textbook is Calc 1, 2, and 3. There is no Calc 4. Like those some of the those
But
books.
it's still Calc, so why don't they just continue with numbers?
I mean, but technically isn't Calc algebra?
So you could
So
say
algebra
algebra 5.
2.2, 3.
That's what I mean. Like it's all math builds on other math, but like they can't keep extending that name. Like pre-calc's called pre-calc because it's literally like the class before calculus, but it involves trig and algebra.
No, we never had a clear separation.
All I remember is
And I
trig.
think she thought none of us really take Calc, so I feel like it was like,
Yeah. Well,
All right.
but she was, to be fair, only what 80%, or 80% of us were.
more than that.
Really, I thought it was just 80.
Yeah.
Yeah, I guess if there's 5 of us that.
So approximate differentials and linearization give approximations. Obviously, they aren't exact. We know that because we've taken some of the things we found and compared them to our calculator. A tangent line is simply a good way to approximate a curve. It gives a relatively good estimate as long as we don't go too far away from the center point. So you asked yesterday, like, why did I pick 121? Why did I pick that 125? That's because those values are close to the center point or the point we are approximating.
So if we had a calculator, we would just be able to type this in.
Correct. Correct. Like
That's another thing I hated. We never had non-calculator tests until this year.
Yeah.
I've started giving them in algebra 2, advanced algebra 2.
Because I relied way too much on it.
You know what
Last
Trinity
year, I
does
feel
that
like I
I
didn't really use that
consider
calculator. But I relied on it. Like, I always
the
made my
highest
own
grade on the
research
test
to
out of
do
the
that.
entire class goes to a chart, and then at the end of the year, whoever has the most in the chart is called the alcoholic
For what? For what?
for calculus over at Trinity.
They
call
still
it-
do that?
Yeah, they call it the alcoholic.
That must be the new teachers because the other teacher I knew left.
Well, I think we know who's winning here.
Consider the function f and label the center point c of f of c and draw the tangent line to the point. So basically we're looking at linearization but as a drawing. And this is like the sum all of applications of derivatives. Because then we're going to look at Riemann sums and we're going to look at area under a curve and taking derivatives backwards. So what is the equation for the tangent line you drew in? So on your graph, you have a point, draw in a tangent line to that point such that it applies that formula.
I just wrote it.
Oh.
It is an underestimate.
What is the equation I put underestimate?
Alex,
What?
in the integral question, did you get 320?
Yeah.
Okay.
I also that wasn't right. That integral question couldn't have been right because it was kx to the it was a fractional thing. It was a fractional integral.
It was like
And
over 2.
I know there was a special rule we had to use and we just didn't for our physics.
You'd
class.
have to show me after. I won't know right now. All right. So then you have the center point. Draw your additional point so that we can understand that the movement from the center point to our new point represents the change in the curve. And this delta x is what we call the differential. That's technically what we've been talking about. This represents the change from point A to point B. And this represents the change in y. So this is the change in x, this is the change in y. The reason we end with differentials and with deltas is that's because that's how we pick up with Riemann sums. Riemann sums represent the width of a rectangle. So we're finding the area of the curve for. Linearization represents the width of the curve that we are finding the tangent line for. I know. I think they're a lot.
I'm like,
So when we talk about differentials, we're talking about the change in x and the change in y. And then what we can do is compare the change we calculate to the actual. So the actual change in y, or delta y, is given by f of c plus delta x. That is what we've been finding up to this point. This is kind of like my x and my a. And that's the answer you get. So that fraction, when you have your work like this, and we do L of x equals f of a plus f prime of a times x minus a, the answer you get here is your delta y. That's the change in your y value. The answer we get in here is my delta x. So the delta y is this answer we get here, because this is the original y. So this value, when you multiply the derivative by the change in y, represents that delta y. And I promise, once we look at a couple examples, it starts to make sense.
I hope Mr. D doesn't have class this period, because I just texted him and he already texted me back.
So when delta x is really, 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 really small, we say that delta x is actually equal to dx. And if you think about dx, that comes from dy over dx. And if you think about what we've been saying a derivative is this whole time, it's the change in y over the change in x, because it's really just the slope. So a differential is when we solve for dy, but we multiply by dx. So if you go back to limits, our limit idea was that we were always trying to get the value of h, or the denominator, really, really close to 0. That was the limit as h approaches 0. If you think about the other example, is the limit as x approaches a, and the denominator was x minus a. So differentials go all the way back to limits and that connection. We're trying to make the limit as h approaches 0. H is my bottom. That's like the dx. My dx is getting infinitely closer and closer to 0. The limit as x approaches a, where you have x minus a, 0. When we did our tables, we did plus 0.001, plus 0.0001. We are adding the smallest fractions of 0.01s to them. That's why a lot of them are 0.1. Because they're really close. That's a small dx. Okay? So it says find the differential dy when dx is 0.01. A very, very small dx. Given that x equals 2 and y equals x to the 5th minus 4x cubed. So what we need is dy dx. So I need my derivative. So derivative of x to the 5th is 5 minus, and if we're trying to find the differential dy, we're going to multiply by dx. And we were given that x is 2 and dx is 0.01.
Is that why it's y is equal to instead of like f of x equal to?
Yeah. So 2 to the 4th, 16. 16 times 5, 80. 2 squared is 4 times 12. So 80 minus 48.
32.
And then 0.01.
Yeah, 2 places, so it'd be 0.32.
Yes. I was going to show you that, like, I can divide it by 100. Yes. So again, if you take 32 times 0.01, 2 decimals, the 1 times everything gives you the same, so you just move it 2 decimals. All right, what does that 0.32 represent? So what part of the tangent line would that be giving me, though? On what? So not 2. That does have to do with 2. But 2 is the original value. What's my delta x? My delta x isn't 2. That's what you have to make the connection with now. So if the original x value is 2, and my dx is, that means my delta x is
2.32.
That's my delta y.
Yeah.
So that's this answer.
So it's 0.01. So 0.32 is showing that. Oh, we just solved the first one.
How would I make this value equal 0.01?
You add 2 to the other side.
So the x value is 2. So that's what I am approximating. That's my linearization. The L of x would be like of 2.01. But the answer that I'm getting, that 0.32, that's not the approximation of 2.01.
Because we didn't even incorporate x.
Exactly.
We're only doing
That is the delta y. So that is the change in y
when x is equal to 0.01. No, 2.01.
Yes, this value right here represents the change in y when x increases by 0.01 from 2.
I thought x is at 2.01 and delta. Right? Like delta x is 0.01, so x is equal to 2.
No.
But, I mean,
dx and delta x are different. D is derivative of x. Delta x is change in x.
But isn't
dx is a change in that final, it is the final change.
When you're talking about a line, but if you're talking about distance or displacement, that's different.
Okay. So in terms of this problem, if this is the graphical aspect,
which is delta x.
our initial condition or our initial point, 5x to the 4th minus 12x squared, so let's assume it has a little bit. Just assume it looks like that. I really have no idea where we are. The initial point you have is 2. When x is 2, 2 to the 5th minus 4 to cube. So take out 2 cube, leave it 2 squared. 4. Really? Doesn't make sense.
Where did you get 25 from?
It's 2 to the 5th.
Oh.
That technique. But the change from the point 2, 0 to 2.01 0.32. The change from 2 to 2.01 is 0.32. It's like rise over run.
So it's not.
This is dy. That's what I was saying. This 0.32 is not the value of y.
But is it the slope of the tangent line in
No.
that change or no?
No.
Okay.
It would be
Because
it would
the
be
slope
high-
of the tangent line was 32. Because
Okay.
this represented the derivative at 2.
I just
So the slope of the tangent line was
So
32.
it would be like the hypotenuse if that was a triangle.
I don't get how
That's what
that.
the 0.32 would be.
The 0.32 is dy. It's the change in y from when x is 2 to when x is
I get what you're saying.
2.01.
So if we actually had the value of 2.01 and we subtracted it
The
from
value
the
of, well, in this case, since 2 is 0,
yeah,
the value at 2.01 is 0.32.
but yeah, it's if we subtract. Yeah, I get
It
what you're
would be
saying
as
now.
if we subtracted it. That's what I'm saying. This one was tricky because it was at 0.
Yeah. So if the value of 2 was 4, the value of 2.01 would be 4.32.
Correct. Which was the answers we've been getting for linearization. This is like the pre-linearization, or like a part of the linearization formula, which is known as the differential. The differential represents the changes. Differential is kind of like how I said, there's something called partial derivatives. Differentials don't represent the entire slope. They represent the differential piece of that slope.
So then if we did 0.32, oh, that makes sense. 0.32 over 0.01 is dy dx.
Exactly.
Oh, that's how you get it. Okay.
Exactly. And if you took 0.32 divided by 0.01, you get 32. Yes.
Okay.
Yes, that's what I was trying to show.
Yeah, but what I'm so after so say if we try to solve for like Lx, where would Lx apply?
So if you turn this into Lx,
Like if we add
Yep,
F
right.
to it?
this would be L of 2.01 equals f of a in this case is 0 plus 32 2.01 minus 2.
Well, we already solved for first, so it would just be 2 plus 0, right?
Yes.
So where would that be?
It wouldn't be.
And
Well,
what is that?
It would be. It would be the x 2.01 comma y 0.32. Let's look at another example before my bell rings. Yeah. All right. Find the differentials. So we're looking for the change in y from point A, which is at pi. So like my starting point is at pi. So the sine of 3 pi is equal to sine of pi, which is equal to 0. So this is my initial starting point. The dx value is negative 0.2. So that means that when I did x minus a, my a is like pi. I need that answer to be negative 0.02. Which means I'm going left of my point.
So it's an overestimate. Yeah.
Because we're going to this point on the graph now. Well, we don't know yet. So the change from here to there is negative 0.02. That's what I'm looking for. I'm looking for, so this is the width. I want to know the height. That's what dy is. It's the height from this point here to our new point.
So then why did Alex say something about
That graph.
He was asking if the hypotenuse would be represented by the equation of the linearization.
Oh, okay.
The hypotenuse would be the linearization equation,
Okay, maybe
which is kind of like the distance
that's
one.
why I was so confused because I thought you were saying that dy is equal to like 3.2, which is the distance, like hypotenuse, but it's the height. Then why was L equal to 0.32 still?
Because f of a was 0. Just like in this case, the sine of a is 0. So my dy is going to be my L of x again. So this says dy equals 3 cosine 3 pi the change is negative 0.02. Cosine of 3 pi is like cosine of pi, which is,
-1.
yep. So you get
Negative
3 times negative 1 times negative 0.02. Exactly. So you get negative 3 times negative 0.02, which was like 3 times 0.02, which is 0.06. That means that the height from here to here is 0.06. So that means that this graph is going this way,
So like
to the left of pi.
So like your height is delta y.
Yes.
This is delta x.
Yes.
And this vertical is L of x.
Yes. Nailed it. All right, you do have textbook homework. It's going to be on that 254, 19 to 25, 31, 33. So 254, 19 to 25, 31, 33.
I'm gonna write it on my planner.
Uh-oh, I'm almost out of
Wait, where
notebook.
did you get the negative
in my
0.02?
fridge.
The dx that was given to me.
I didn't think you could just
So we
multiply
don't need to do
dx
x
over.
minus a because x minus
They
a
didn't
equals
give you an x. Yeah, we don't have the x minus.
That's why I was so confused. I was like, where's x minus a? But we know x minus a is equal to delta x, and we know what delta x is.
Alright, Mr. Bragg, real quick. So it was spring constant kx to the 4th over 2.
Oh, here it is.
Oh, you wanna write it on that?
Just any variable.
Oh, spring
so
constant.
any variable you choose that's not x. Kx to the 4th over 2.
Alex, k is 100, so you could do 100 divided by 2, which would be 50 x to the
Are we
4th.
integrating this?
50.
Do I have bounds?
0
0
to
2. I'm telling you, isn't
So
k
k over 2,
K
k
was
is a
100.
constant, will come out in front. So it'd be like the integral of 0 to 2 of x to the 4th.
That's not what I did.
So that it would be k over 2. So you
X
add
to the
1,
5th over
so it's
5.
x to the 1 over 5
So that's
from 2 to 0. The 0 doesn't matter because it's going to go away. So it'd be k over 2 times 2 to the 5th, which is 32, divided by 2, which is 16.
times 100.
So it'd be 16k, or